today's presentation is Antihistamine Medications, a history and in-depth comparison. According to the CDC, an allergic condition is a hypersensitivity disorder in which the immune system reacts to substances in the environment that are normally considered harmless by releasing histamine from the tissues. The most common allergic diseases include hay fever, asthma, conjunctivitis, hives, eczema, dermatitis, and sinusitis. Hay fever, an allergy caused by pollen or dust in which the mucous membranes of the eyes and nose are itchy and inflamed, causes a runny nose and watery eyes. Anaphylaxis is the most severe allergic reaction. Symptoms include tingling of the palms of the hands, soles of the feet or lips, lightheadedness, and chest tightness. According to the CDC, in 2015 in the United States, children 18 and under had the following statistics. 6.1 million reported hay fever, 7.4 with respiratory allergies, 4.2 with food allergies, 8.8 with skin allergies. Alternatively, adults, 20 million reported hay fever, or 8.2% of the population. Globally, hay fever is experienced by 10 to 30% of the adult population. It is important to note that the percent afflicted varies across different racial, ethnic, and socioeconomic status groups, but in general, the trend is rising. First-generation H1 antihistamines, the focus of today's presentation, for example, Benadryl, refer to compounds that inhibit the activity of the H1 receptor, which are present on nerve endings, smooth muscles, and glandular cells. H1 antihistamines are inverse agonists, thus they do not antagonize the binding of histamine, but rather competitively bind to the same site on the receptor to produce the opposite effect, by reducing overall activity. H1 receptors are part of the family of the GC protein-coupled receptors. GPCRs provide a means of communication across the membrane. When a ligand binds on the extracellular side of a GPCR, the conformation of the receptor protein changes on the intracellular side. The conformation change causes the release of proteins into the cytosol. These released proteins transmit the signal of the ligand, still on the outside of the cell, and ultimately causes a cellular change. Alternatively, H2 antihistamines work by blocking histamine released by ECL cells in the stomach from binding to parietal cell H2 receptors, which stimulate acid secretion. Therefore, other substances that promote acid secretion have a reduced effect on parietal cells when the H2 receptors are blocked. When immunoglobulin E, IgE, binds to an antigen, it will degranulate and activate mast cells that release histamine, ATP, and other mediators. Histamine activates H1 receptors and thereby the NF-κB transcription factor, which regulates inflammation, causing allergic reactions, infections, and free radicals. H1 antihistamines displace histamine from the H1 receptor. It also prevents the formation of IP3 and a release of stored calcium ions. Similarly, H2 antihistamines displace histamine from the H2 receptor, avoiding the activation of CAMP. H2 blockers ultimately lead to a decrease in CAMP and a consequential decrease in calcium ions. A decrease in calcium ions is significant because an influx of calcium ions and the subsequent activation of calcium-dependent enzymes are crucial to the propagation of the mast cell mediator release cascade that results in the release of histamine.
Histamines are ligands released from mast cells which bind to G protein-coupled receptors, designated H1 to H4. For the purposes of our presentation, we are focusing on the H1 receptor. H1 receptors are expressed in nerve cells, airway and vascular smooth muscle, endothelial and epithelial cells. They are also expressed in brain neurotransmitters, which affect the sleep-wake cycle, causing drowsiness. The general function of H1 receptors are inflammation and an immune response, hypotension, which is low blood pressure, headache, flushing, bronchoconstriction, which is tightening of airways and lungs, and stimulation of cough receptors. The general structure of a histamine is an aryl ring, as you can see below, with a small carbon chain and an amine. This provides a scaffold for antihistamine structure.
Antihistamines are a class of compounds that stop the action of histamine in the body. Within this class of compounds are two types of antihistamines that work at the H1 receptor. These are broken up into first and second generation drugs. Both generations seek to treat the same symptoms, but may have different side effects or activities. This will be discussed in further detail later on. H1 antihistamines will be the focus of this discussion, since compounds that work at the H2 receptor treat different symptoms, usually gastrointestinal problems, than those associated with the H1 receptor, such as allergies or hay fever. The general molecular structure for an H1 antihistamine is shown here, and includes two aryl groups connected to each other and linked to an amine group through a carbon-based spacer. Antihistamines can be administered in several different forms, but they retain the same general structure in all forms. Typically, the oral drug is preferred, but they are also used in the form of eye drops or nose sprays. They can be applied topically as well in the form of creams or gels. First-generation antihistamines, such as diphenhydramine or Benadryl, have similar half-lives to the second-generation drugs, but have shorter therapeutic effects. These can be taken roughly every 4 to 6 hours, while most second-generation drugs are taken once daily. Although diphenhydramine is likely the most well-known, other first-generation compounds that display similar core structure but higher functionality, such as bromodiphenhydramine, are more potent as antihistamines. Second-generation antihistamines are less likely to cause drowsiness because they are ionized at biological pH, and they are too polar to pass the blood-brain barrier. Many second-generation compounds have active metabolites, which contributes to their prolonged therapeutic effect over those of the first generation. In addition, because second-generation drugs are developed to have both higher bioavailability and more specific activities, a lower dose can be prescribed to achieve the same therapeutic effect. Interesting to note is that the drugs which have the highest revenue in the US are primarily second generation. In fact, the only first generation drug represented here is Benadryl, suggesting that the more optimized second generation drugs are more popular and highly circuited than the original group of antihistamines.
Daniel Beauvais, in the 20th century, at the famous Pasteur Institute in France. One of his predecessors, Ernest Fourneau, had cataloged thousands of chemicals in his work on finding an active anticholinergic compound. Beauvais recognized the structural similarities between epinephrine, histamine, and the well-studied acetylcholine. He began looking for a histamine antagonist using the vast chemical library of Fourneau. Eventually, Beauvais found that the phenolic ethyramines were the most potent at inhibiting histamine poisoning in guinea pigs. These animal phase 2 trials show that histamine inhibition is closely tied to acetylcholine inhibition. Thus, the first antihistamines were actually repurposed drugs from a similar class. Beginning with the phenolic ethyramine in the top left corner, compound 928F, which offered no protection against histamine poisoning, Beauvais and his assistant Anna-Marie Straub improved potency with various phenolic substitutions. The figure here, taken from their 1937 publication, shows that an orthoisopropyl and a metamethyl variant called 929F offered protection from the most back-to-back histamine treatments. This compound still had remarkably low potency, requiring 40 milligrams per kilogram injections to have an effect. A major side effect was substantial sedation, explained by the high lipophilicity, allowing it to cross the blood-brain barrier. Because histamine also interacts with the central nervous's wake-sleep cycle, 929F caused the drowsiness that is equated with early antihistamine activity. A second structural motif that Beauvais and Straub tried changing was the type of phenolic connection to the alkylamine. This method was borrowed directly from Fourneau's improvements in his own studies. Beauvais spent 4 years and over 300,000 tests to result in the most optimized compound. Beauvais found that an aniline connection proved the most potent. Because of how early this work was in the medicinal chemistry timeline, Beauvais was not hindered by the structural alert that accompanies anilines today. This proved not to be an issue, resulting in the first commercially successful antihistamine Antergan. A separate optimization pathway resulted in the highly successful diphenhydramine or Benadryl from a research team in the United States. All these compounds, despite different optimization pathways, have similar structures, a large side of aerial rings and a long alkylamine chain, as necessitated by the binding pocket of the target. Using CSAR to model the H1 receptor protein binding to both the native histamine seen in the top picture and Benadryl posed in the bottom picture, the two compounds have nearly identical poses within the binding site. As expected, the affinity of Benadryl is higher than the histamine so that it can competitively inhibit the protein despite the presence of histamine. CSAR predicted that both compounds form a hydrogen bond between an N hydrogen and aspartic acid 107. This complies with recent literature stating that this residue is highly conserved throughout H1 receptors in various species and is thought to be essential for proper binding. Optimizing histamine itself by adding two methyls onto the nitrogen and adding a phenyl near the imidazole ring increased its binding affinity significantly. This happened because these structures filled more of the binding pocket, better orienting the N hydrogen to interact with the aspartic acid. This explains why Benadryl has such a high affinity than histamine itself, since it has fewer degrees of freedom in its orientation.
Because Benadryl was so successful, it has much more information readily available than its early competitors. Benadryl is quite lipophilic, with a log p-value of 3.3, which is necessary since its target is a membrane-bound G protein receptor. This lipophilicity results in a high volume of distribution of 3.28 liters per kilogram and a long half-life of 9.2 hours. Benadryl is almost entirely metabolized in the liver, meaning that its total clearance is equal to hepatic clearance. The oral version of the drug has a 70% bioavailability, with about 50% of it being metabolized in first pass effect before reaching the systemic circulation. Of course, this can be improved by taking the drug as IV or through the skin as a cream. The drug is broken down by demethylating the amine and oxidation until its metabolites are excreted in the urine. Some side effects of antihistamines have been favorably altered to produce new drugs, a method similar to selective optimization of site activities, or SOSA. Marzine and diphenhydramine form as Dramamine, which is used as antiemetics for travel sickness. Antihistamines are modeled after Fournot's anticholinergic drugs, which can downregulate nervous response as mild treatment for Parkinson's disease. Antihistamines arose based on their similarities to other drugs at the time and continue to be repurposed as new possibilities arise. They left a significant impact in the medicinal chemistry process, earning Beauvais a Nobel Prize in medicine in 1957. Due to their long history, antihistamines have been well studied and are strong examples of the interaction between compound structure and therapeutic function.